Last week before, section 3.2, I want to make a correction. Your notes are perfectly fine. 3.2, the equation set I went through, I have done that some years back. No change on that, but I myself a little bit confused on this following equation on that. So I made a correction, but I reconfirmed in the conference. Then I want to use 3.2 as is. The reason I kind of confused even myself is as follows. I'm going to introduce a couple of parameters, which is called the sensitive parameter, or that's unclassified both. But another parameter is a shock factor. You may not hear about the shock factor. Shock factor, this is a measure of the damage on the ship. So shock factor or sensitive parameter. But this is more popular. But if you go into even internet and type this in, you will see the equation. This parameter is a measure. This is a measure of damage. Okay, this is a measure of damage. Equation form goes like this. Equation form, shock factor is equal to square root of W over the R. Okay. So you have, let's say, submarine here. Just the cross section you are dealing with, and the target is there. This is a target, and this is a source. Explosive is here. Explosive charge is W, and the distance is R. Some people is talking about is R to the center or nearest point of the hull. I would say nearest point of the hull, but really doesn't matter. Usually this R is much larger than the radius of the target. Okay, so whether you use up to here as R, up to here as R, really doesn't matter. But if you ask me to pick, I'll pick the nearest point. Okay? So W here is equivalent charge weight of TNT. Everything converted back to TNT. These equations, okay? So R is, this is in pound. It's unit dependent. It's in pound, okay? And R is standoff distance. Standoff distance in feet. So this the shock factor has units in there. So this is a pound, and this is R. Okay? But in a sense, as you saw in the scaling in chapter 4, the W, if you look at as a unit, W is the volume, is G, rho G times the volume. You remember? Okay, the volume is L cube. Not clear? You have exam last week. So here, for the unit wise, here is proportional to square root of L cube over, this is L. Make sense? Makes sense. And this guy, if you look at that, this is L times square root of L times L. If you look at this, unit-wise, this guy is like something like this. It's not the unitless. So that's why I don't know what they do in Korea or other countries who use the metrics, but this is again use the pound and feet system to determine the shock factor, which is a measure of the damage of the ship. Not clearly known how this is really works. Well, in equation form is clear, but the measure you need to conduct the testing to fit in to the right place. Anyway, this is what the W is, equivalent charge weight of TNT. If you have, let's say, 10 pound HBX1, you should not put 10 here. You have to multiply something like 1.4. Some people say strength is 1.4 times TNT. I usually use 1.5. So you have to use, if this is a TNT itself, then just use a 10. You should follow, okay? And this is for this submarine situation. But what about the surface ship? Surface ship need a slight modification. You wrote it down, right? It's not in your note. Okay. In a surface ship, a ship is in neutral buoyancy, floating at the free surface. So you have like this. This is, of course, you call the keel line. The keel is at the bottom of the ship. And I can put the charge here. This is charge. Of course, this is W. And now you can put the distance to the key line. Then you can call this is R. And this is that I can draw the line here. And this is the angle theta. For surface ship. For surface ship, use a keel shock factor. SF. SF is equal to still W over R, half of 1 plus sine theta. Okay? Again, definition is the same. W is equivalent charge weight of TNT, and R is a standoff distance to the key line. And this is not the unitless, it has a unit in there. And what happen if theta is 90 degree, which means the charge is right below the keel? And what is it? What's the shock factor? Charong. What's the shock factor if this is right below the keel? You decided not to talk Monday morning? That's it. This is 90 degrees. Sine 90 degree is what? Charong, what? 1. 1 plus 1, 2. 2 over 2 is 1. So, if the theta is 90 degree, then shock factor is really, which is same as like a submarine situations. Okay. Then your question would be, how did you get there? How you have to say something on the shock factor like a 1 or half or 0.2 or whatever, which comes from the experiment. The US has done a lot of experiment. Just a general rule of the thumb. Otherwise, it's all in the classified domain, which I can't talk. So for the equipment, rough range is about 0.3 for the shock factor. For the preventive measure, so for the equipment, shipboard equipment, typical yardstick value is about 0.3. And for the ship itself, it varies. Could it be 0.5 to 1? It will go beyond 1 at all. It's going to be maximum to be 1. Okay? So but one of the drawbacks in Korea is they don't have many on-deck test data. So I'm really telling to defense, like Department of Navy here, they must perform more testing and more testing. But modeling and simulations are the mandatory. You have to do that. Then the other hand, you have to really conduct the testing. Start from the small charge, small structure to the large. US, the strong point is they are doing it. They put the newly built, as you saw last Tuesday, DDG-81. That ship, I was working that ship for about 2 years to get the modeling and simulation. So how? They are doing, they have scheduled to conduct the testing. then I'm in charge of modeling and simulation. That means shipwreck trial simulation, as you saw. Not after they conduct the testing. Before the shock testing, my students and my research fellow, myself, are doing all the simulation. Then generate all the result. Then put that in to Department of Navy. Then they conduct the testing. Then they brought all the test data. Then they compare. They compare. Then once they start to compare, they provide us the test data. Then we start to compare too. That's very fair. But if you do the modeling and simulation after they perform the testing, it's not good, because reliability is a problem. Hey, we conducted testing already. Gosh, then you're doing it? Have you seen the result? So such a some sticky issue there. So we always conduct modeling and simulation beforehand. And other kind of the big project we involve, you know, they have done, they are scheduled to conduct another testing from the DNA, Defense Nuclear Agency. We had a project that we submit all the simulation result, then they compare. After they conducted testing, it was really sometimes a nightmare. So sometimes the simulation result is quite different from test result. That's why as you take this course, put that in your mind. A lot of people here, and also other nations other than US, they feel simulation can do everything. No, simulation cannot do everything. You have to keep the compare, and if it's different, you have to find out why the results are so much different. That's what the important thing is. So here is shock factor. Remember this. This is applied to the surface ship. Without this is submarine situations. Okay. And also, I want to point out this. I want to make corrections. Okay. This is when I pull out, it's let me see whether I have it here. You had this last week. All the equation built in the chapter 3.2, all the equations, okay? All this equation, not only P, there's W here, theta W here, all the equation there, all the empirical equation, I impulse there, E energy there, T is there, associate with this K A factors. All the equations in the one thing I confused was I want to ask you accept my apology, because this W And this W is a charge weight. If you use TNT, then you use the associate K2A2 from the table. But I told you 2 weeks ago or 2.5 weeks ago, I said use TNT equivalent charge rate. I'm confused with this. But your notes, everything is correct as is, okay? But if you multiply the factor on problem number 4 in the exam problem, if you multiply, I think it's HBX1, right? So that's okay, I'll accept it as is. But in the correct sense, whatever associate with the different charge type, in this empirical equation, it should be W should be the charge weight as per the charge type. If charge type is HBX1, you're going to use corresponding the K value and A value. You follow me? Then that's what you have to use. We'll do some exercise today too. No confusion. But some equation, I'll point out from now on what equation you have to be careful to use equivalent charge weight. This shock factor, you have to use equivalent charge weight, not this. Because this is already there, saying that this is associated to particular charge type. So use that as is. If you look at this bodily response means you have, let's say, this is really submarine related one. Then this is submarine. Its beam-like structure is long. If you look at internet, there are a lot of information on U.S. submarine and Russian submarine, which is not, some of them of course very much classified, but basic configuration is not classified. This length is not classified. A whole different type of the submarine they have. And surface ship is the same thing. Of course, a lot of weapons, almost all the weapon system in the ship and submarines are classified, but length of the ship is not quite classified. Like a submarine, all different kind, attack submarines, or the submarine which carries the missiles and all that, the length is something like 300 feet to 500 feet, vice versa. And cross section, I'm not going to talk about it, but you can also find out. And the one case is you want to see the motion of the submarine at the time of explosion. Sometimes you want to see the motion of the surface ship at the time of explosion. You compute it, even in the exam, last problem, the kickoff velocity. So kickoff velocity is the motion of the surface ship at the time of explosion. So this bodily response means treat the boat as rigid and calculate the motion. It's very important. When you do the dynamic analysis of satellite, which is in the orbit, it's the same thing. First, you want to really see the motion of the satellite, treating the satellite as rigid. Then you want to find out how the motions along the orbit would be. Then after that, when you design the structure of satellite itself, then you are talking about the deformation of the shell. Same thing in the ocean structure. First, the task is what would be the response due to the shock, thinking the body as a rigid body. Okay? Then second is, okay, for shock, when you closely look at the ship or the submarine, what would be the stress and deformation of the components and the whole system. So that's what you are looking here is bodily response means really response to treat the ship and the submarine as the rigid body, okay? But there is some historical things I spelled out here. But one thing clear for the bodily response of the submarine, you must use, I can just, I don't have to explain. This is just somewhat historical. You must treat the shock wave as a spherical wave, not a plane wave. Especially, what does it mean? In a plane wave, there is no curvature is infinite. It's a plane wave and hitting it. Okay? So for submarine, insisting use this equation. Have you seen this equation before in your life? Yanok said so. How about Hassan?
This equation was given actually in the exam. In the exam paper, this equation was given.
You saw this or not?
Yeah, I see this.
Lee?
Yes.
Willis? You all saw that because it's right after midterm exam. If you don't see that, you have a problem because you have a relevant equation. This is a relation between the shock pressure and fluid particle velocity, or treat the ship or submarine as a particle because it's rigid to compute the bodily response. So here, if you don't have a second term, this is exactly for what wave? Plane wave, right? P is equal to rho cu, right? Without the second term, U is equal to P over the rho C, right? Young right? And this second term is called what? Afterflow term or the surge term. And I mentioned that's quite significant. How much is significant? Maybe 10% of total. Sometimes that's a significant. And when R is very large, then what happened? Second term? Someone? What second term would it do? You can neglect. Why? Because 1 over large value, R. So second term diminishes. Whatever that is, second term is the effect of the curvature of the shock wave front, right? Right? Shock wave front. So shock wave front, that's what this, sometimes this is called surge term, S-U-R-G, and integration is from starting time to the current time, for it matters on the history of the shock wave. It diminishes, right? P is equal to P max, right? Times e to the minus t over theta. Got it? It's what the function of the t. So kind of insisting here, you must consider the spherical charge. Over here, the t, the reference time for t, if I just write this way rather than t minus t1, reference time is the time the shock wave hit the target. Then you start to count, right? So, make sense? Your eyes doesn't approve it. Ooh. Yes or no? So when you do the integration, you end up having the form is P max over rho r theta all this. P max is, you know, in chapter 3.2, you know P max is empirical formula, right? As a function of charge weight and standoff distance and charge type. Okay, that you have to remember that. So then next page I just wrote this. First I generate this, my just handwritten note. Then I typed up the page just the before, just to shown just before. So here, simple integration. That's all I'm doing here. And then integration, you have that. And as you see there, same approach here. So this is charge, this is a target, then this is incident shock wave. So due to the incident shock wave, what happened? This target is going to move in the same direction. And now this could be shallow. If this is a shallow water, then the reflection would occur, right? Hit it, then bounce back. Then you put the mirror image, exactly the same way as we have done for free surface. Then image charge, you draw the line, and this is down, hit the point on the sea bottom, then reflect, and going this way. This is a compressive wave. This guy is louder. Lee, compressive or tensile? Huh? Really? Compressive. Except this. Everything is compressive. And then this guy will hit, bounce back, compressing the water, bounce back. The shock wave direction is same direction as fluid particle. This way and hit it. So you have one component here to compute the velocity. You have another component going that direction due to the shock wave coming from the sea bottom. If this is blue water, then it's a bottomless. Blue water means it's a bottomless. Then you don't have this component of the velocity coming from the sea bottom so deep. By the time it comes back, it's meaningless. Okay. Then another wave is coming back from the image charge here. This is a free surface, and connecting here, then you can see coming, hit the free surface, then coming back down, right? That wave is tensile wave. Okay? tensile wave until this guy hit here, hit this just before. That's what you have to compute the fluid particle velocity. Fluid particle is moving toward his girlfriend, right? It's all going up toward the image charge, but shock wave front, right? Rarefaction wave front. Surface reflection wave front is coming down to the target. Fluid particle is going in that direction. So you have another component, 1, 2, 3, okay? You have to combine them by the vector sense, not the scalar. If it's a shock pressure, then you can just add them together algebraically. But velocity is a vector component. You have to add in a vectorial sense, okay? That would be the resultant direction. And the corresponding, the target velocity, you can compute that. And this is again the pressure versus time. It could be like this, depend on the location. It could go up to the max, and the time, reference time is the time the shock wave hit the target, because it's a 0. Then exponential decay, suddenly it could cut off below 0, but water cannot sustain the tension. Then you can reset to 0, then stay in 0, then going back up, like bottom reflections, whatever, because arrival time, by the way, arrival time is all different. Arrival time is all different. For the shock wave is concerned, this may be shortest distance, then this will, that shock wave hit the target first, then it's going to go away, right? And this guy depend on the depth relation, maybe the distance between this and distance between that, you have to compare, right? Then you can determine which one comes second, and which one would come the third. You follow me? Then you have to decide. So first one would be, this is pressure versus time t, okay? First one would be bang and done. Then when it comes, when I write this way, I should do like this. So this guy is PA plus, I call the pH, right? This is incident shock wave. Then now, if I draw the rarefaction wave, surface reflection wave, it could be, let's say, like that. It's gonna go down 0. Rarefaction wave. So next is maybe bottom. Let's say this is longest one. If you say that's the longest one, it's not going to happen right at cutoff. It could be some other time. Could be like that. I'm sorry. That's not the negative pressure. That could be like this. So you have to add them all together. If you do that, so resultant is goes up. This is a P max. or sometimes I use a P naught. Then coming back down, then you have to add here, even if it goes below 0 when you add algebraically, it's not going to go below 0. The lowest it can go is right here, right? Then it's going to cut like this, stay 0. Then now that's from the bottom reflection, so that plus that much, you have to add that much right here. Okay? So you have to keep adding, which is parallel to this. So go up. It's not going to go below this guy, so it's going to stay like that. Questions? Very clear. Adding together in different time. This is pressure experienced by the target. For motion-wise, target, and this could be first one, second could be this, third could be this. So you have to have a vector sum. You can compute the U1, U2, U3 vector sum. You can set, it's just a vector sum. Usually trajectory of X, trajectory of Y. Then you can just have U, X component, UY component, simply vector sum. So resultant value is UX squared plus UY squared is what the target is. You need to do that. This is for the vehicle in underwater, like a submarine. This section is for that. And this is a 1,200 HBX1 for shock testing. Okay, so this is unclassified because you don't see any floating structure, nothing. But it shows a sample measured velocity here. And for 1,200 HBX1, then this is actual experimental data. And we plotted it together without afterflow, without the second term. This is with the second term. So second term is quite significant. If you look at just the first term, like this one, it's really off from the experimental data. But including the second term, this fits much better. So keep that in mind. Using the spherical, the wavefront provide a lot better compared with the experimental data. Okay, this case is the R, the standoff distance, has to be not 1,000 feet away. Forget it. This converges to this because the second term effect is almost none because it's proportional to 1 over R.